where communication has to get into the communication medium, or a message, once it has been prepared, it has to get into the communication medium for it to be moved across the network, be it the local area network or the wide area network, until it gets to the intended recipient. And that is where you find the physical layer, where we are starting our discussion today. That is why I'm inviting you for this presentation, just to understand what usually happens at the physical layer. So our purpose for this today's class is to understand how the physical layer behaves, or how it is normally represented. At the physical layer, another thing to note is that you can have the physical layer represented by the physical connections, or it can be represented by the wireless connection. So here in this discussion, we are looking at the physical connection and what usually happens. That is why we are talking about the UTP, the fiber cable, or the coaxial cable. When we have them represented this way, we normally talk of these representations as the standards for Ethernet. Ethernet is a protocol representation which is a combination of many other protocols. As data is moving, that is a lecture I will share later on the OSI model. As the data is moving from the application layer through the presentation layer, the session layer, the network layer up to the physical layer, there are what we call encapsulation, or data that is added into the main data which is being communicated. And that encapsulated information is supposed to ensure that this data being transmitted is transmitted the right way, and it is going to reach the intended destination. That is why we talk of the Ethernet standard being a group of protocols which is going to enable data to be moved from one point to the other by use of different protocols. You can see that maybe at the network layer, you normally add the IP address. Maybe at the internet layer, there is also another information that is added, and it is added that way so that information is moved. But I will share that information in another class. So I will do a recording for the sake of the people who have not been able to attend the classes, so that we can move together. So here we are looking at the Ethernet standard, whereby there is going to be physical layer implementations. And the four common physical layer implementations include the 10 base 5, the 10 base 2, the 10 base T, and the 10 base F. So the most important, there is also a new one, which is 100 base 10. Now, the most important thing to understand is, what does this 10 represent? What does this base represent? And what does maybe the 5 represent? So if it is at 10, it means that the transmission speed is going to be at 10 megabits per second, for instance, or 10 megabits per second, yes. And then the base is supposed to talk about the baseband representation of data, and then the 5 is supposed to look at the standard of that cable, which could be coaxial cable standard 5, or base 2, which is standard 2, and that is something we shall look at separately as well. So up to there, at least everybody is up to speed. I hope now everybody is clear on where we have come from and where we are moving. So as I move on, any question or anybody lost where we are? David, are we together up to there? Sami? Macharia?
Niko sawa.
Good, good. So let us move on. So at the physical layer, there are two activities which normally happen. One of them is what we'll call encoding, and the other one is what we call decoding. So when we are talking about encoding and decoding, what exactly does it mean? As data moves from the application layer down the OSI model, it normally is changed, or it is normally represented. At the application layer, it is the normal language that we understand. But when it comes to the presentation layer, there is something that happens, which is translation. That data is translated into digital signals. So that is where data is normally changed, where we are talking about data being represented as either digital or analog. So within the computer, that data is going to be digital. Digital, it means that data is being represented by bits. Bits are represented by either a 1 or a 0. So that is the normal language which the computer would understand, and that is how data is represented. Then as it comes to the physical layer, it has to be translated into a format that can be transmitted on the network. If we are talking about a cabled network or a wired network, that data is going to be translated into maybe electric signals. If it is the wireless, it is going to be converted into analog signals for transmission. Now, that conversion or that data representation, because if it is going to be converted into electric signals, mostly you will find that it is going to be either represented as, if it is a 1 bit, it is going to be represented as a state of current flowing. If it is a 0, it is going to be represented as no current flowing through the cable. So that representation is what we call encoding. Data being attached to maybe the electric current that is flowing so that it can be transmitted. When it gets to the destination, then it has to be decoded. And decoding is what we mean by now changing it from those electric signals or analog signals back into the digital data that can be read by the computer system. And that is what we mean by encoding and decoding. Hope that is clear. Then we go to line coding. Now, when we are talking about line coding, now it is the process of converting digital to digital signals. Because like we have said, if it is digital data, it is going to be converted into some electric current, which are also digital in a way. Because when the current is flowing, there is going to be a 1. When there is no current, it is going to be a 0. And we will see this in a short while. And that becomes line coding. And that is where we are going to convert a sequence of bits into a digital signal. At the sender side, the digital data is encoded into a digital signal, and at the receiver side, the data is created back by decoding the digital signal. So those line coding mechanisms can be categorized into 5. And here they are. They normally have some of the common characteristic, whereby they should be self-synchronizing. When we talk about self-synchronizing, is that both the sender and the receiver should be synchronized. Like, for instance, what was configured at the sender side? If you said that a 1 bit is going to be represented by a flow of current, then at the receiver, that should be the same case. It should not be the opposite. That is what we mean by being synchronized. There should be some error detecting capability. So in both or in all of those line coding mechanisms, you need to have some error detection mechanism so that if data has been interrupted or during the transmission process there have been some impairment or there have been some noise which have been detected and affected that data, then there should be an error mechanism that can be able to note it and if possible correct that error, and that we are going to see. Then that mechanism should have immunity to noise and interference. That means that any mechanism that we are going to use, it should be immune to noise. Noise is any unwanted transmission that is going to affect the current transmission you are making. And one of the reasons why we have these many categories of these mechanisms is because some are just improvements of what has been implemented previously. And they keep on being improved so that they can cancel noise or they can be immune to interference. Then we also say that there should be less complexity. They should be as simple as possible, meaning that the way they are going to encode and decode the data should be simple. And it is because if it is complex, then it is going to mean that you are taking a lot of processing time to do the encoding and decoding, and that is something which is valuable. It is a resource that needs to be valued in a computer system. Then there should be no low frequency component, that is a DC component, and we will see how this happens and how it can be corrected. And then there should be less baseline wandering. Baseline wandering comes from how those signals are going to be spread across from the transmission medium, and we will also look at that. So the types we are talking about, we usually have the unipolar scheme, which is represented by the non-return to zero scheme. Then the polar scheme, which we normally talk of non-return to zero with level, non-return to zero inverted, return to zero by phase Manchester, and differential Manchester encoding scheme. We also have bipolar, which is represented by AMI and pseudoantennary. Then we also have the multi-level and multi-transition mechanisms. So let us look at some of these. We start with the unipolar scheme, where we start with the non-return to zero. And in this scheme, all of the signal levels are either above or below the axis. So here we have the axis, which we normally represent the waveform. If you looked at lecture 2 and lecture 3, it talked about the waveform. And our waveform will usually have the amplitude on this side, that is on the vertical side, and on the horizontal side is time. And we normally said that when a signal is moving or when there is propagation happening, it is going to be measured in terms of time. That is, even when we talk about transmission rate, we talk of bits per second, meaning that in 1 second, how many bits are going to be transmitted? That is why the factor of time is very important. And so here is the point zero, where there is going to be that demarcation. On this side, it is the positive side. Below the zero mark is the negative side. So we are saying for this non-return to zero scheme, it will either operate on this upper side or either on this lower side. And what happens, we are going to have a high amplitude for one and a zero amplitude for zero. And that is how that data is going to be represented. So if the data is 10110, this is how it would be represented in the waveform, such that a 1 is going to be a positive amplitude, a 0 is going to be a zero amplitude, meaning that it doesn't go up. And a 1 again is a positive amplitude, and so on. So that scheme is as simple as that. Then its biggest undoing, or the reason why it looks very simple, but one of the reasons why it is not so popular is because it uses more power compared to the polar scheme to send 1 bit per unit line resistance. So that is one of the undoing. And then if you have a continuous set of zeros and ones, like we have seen here, you have a continuous set of ones or zeros, then you're going to have a problem where self-synchronization and baseline wandering are going to be a problem. Like we have said, these are things you need to avoid when you are selecting an encoding scheme. So that is why it is not so popular. And that is why there have been other schemes that have been developed. So let us look at those other schemes. These other schemes are going to operate on both sides of the waveform. or they will be above and below the zero level of the waveform. And these polar schemes normally take the both sides of the axis, and we have the non-return to zero level and non-return to zero inverted as the first two. And they are similar to the unipolar non-return to zero, but they are going to have the two levels of amplitude, meaning that you can have the positive voltage and the negative voltage as well. So then on return to zero level, the one we are calling L, the level of the voltage determines the value of the bit. So if we are going to have a binary one, it is going to maybe map to a logic level I, and a binary zero is going to be a logic level low. We shall see that. Then if it is non-return to zero inverted, then it is the other side, whereby a one is going to be on the other side uh, of the waveform, and a zero is going to be on the other side. Here is the example, whereby we are having these two. So this is the non-return to zero level, whereby if you say a zero, it is going to be at the top, it is going to be having a positive voltage, then a one will take the opposite side, whereby it is going to be on the other side, a zero like that, a one on the other side. But like you can see, it is going to be affected by the baseline wandering and a synchronization challenge, compared to the other one, whereby you're going to have a zero, and then you're going to have an inversion, whereby one will go down, but before you get to again to zero, then you operate at the lower level until where you're going to find another switch for a one. So you notice here, if it is going to be a zero, then you are not changing. But if it is a one, like here there was a zero, which we started with, then you come down when there is a one, but since it is a zero, you are not going to change like we have changed here. It is going to remain down here until you find another one, then you move up. That is what we call the non-return to zero inverted. Again, since there is another one, you are going to switch. Again, another one, you switch again. Where there is a zero, you don't switch. I hope that is clear. Okay, let us continue. We have the return to zero, whereby it uses three values. If you notice in these previous schemes, we have used two values, either a positive value here or a zero, like the first one, or a negative value. So it is either a positive or a negative or a zero. But now, when we come to return to zero, it is going to use the positive, the negative, and the zero values. So that is where the return to zero has a big difference. And now you will find that in this logic, we are using to represent, or we are representing a bit, a one bit, a half of the signal is going to be a positive value, and a half of the signal is going to be a zero value, and then the signal is represented by a negative value or a half of it. So let's take, this is the data which we are talking about. So as much as we are saying it is going to require a greater bandwidth, this is how it works. If it is a zero, we have said a zero is going to be on the negative side, a half of it, and then on the zero side, a half of it. Then a one is going to be on the positive side, a half of it, and on the zero side, a half of it. The same with another zero. So it is going to bring about the synchronization aspect, but like we have said here, it is going to consume greater bandwidth because you are using three levels. Imagine here you are using two levels, so no much bandwidth is used, but here you are using three levels. That is why we are seeing that difference. Any questions so far? Any question?
Sorry. Um, I think
Uh-huh.
my question would be that slide number 8.
Okay.
Yes.
Uh-huh.
I didn't get very well the concept of now from 0,
Mm-hmm.
it maintains. So long as it's maintaining on 0, it doesn't change after changing to 1, because it has changed to 1, then it maintains on 0. Then if there is a change
Yeah.
to 1, then it changes, and
Yes.
also maintains at 1. So it goes on the is to below 0.
Okay. What we have
Okay,
said,
but yes,
these are two schemes represented here. This is
yes,
non-return to zero level. This
yes,
is
and return to 0,
return to zero
return to
inverted.
0. Yes.
Yes.
Now the bottom one, return to 0 inverted.
Yes.
From this
This,
point of, yes, from the point
what?
of,
Uh-huh.
from the point of when it is returning to 1,
Yes.
that is after the 0 0, maintaining 0.
So what usually happens, so you see this
Yes,
data is the same piece of data, which is 0 1 0 0 1 1 0. Sindio.
yes,
So
yes,
what happens is that in this scheme, you have started by saying that a 0 will start at a positive voltage. Normally it is 5
yes,
volts. Sindio. So it
yes,
starts at
yes,
positive voltage by 5. Now,
yes,
because we call it non-return to zero, these both schemes, they are called NRZ, non-return to zero, meaning that there is no one point they are going to stop at this zero level. Unaona?
yes,
Hii
yes,
mstari iko hapa, that is the zero level. So it
low
means
level.
ikienda kupata another type of data, another bit of
Mm,
data, this is bit
yeah,
moja, si ndio? Bit ya pili,
yes,
it becomes what? A one. That
one,
it is going to switch. Mahali kuna one, it is going to switch. So it
yes,
switches to negative 5 volts because at this lower level, it is the negative voltage.
yes.
Umeshikanisha? Then,
Okay,
whenever there is a zero, it is not going to switch. Sawa sawa.
okay, yes,
So, when it finds a zero, no switching. It continues on that level. Another zero, it is not switching like we have done on the top one. So it is not switching. It continues on the negative voltage level. Then when it defines a one, then it switches to the positive level up
because it
there.
has been on the negative voltage.
Yes. So it switches to the positive level. Again, it
Yes,
defines another one because the rule is when you find a one bit, you have to switch. Then it
you have to
switches
switch.
again. Eh.
Okay.
When it defines another one, it switches again. That is why you see here there is this kind
Um.
of movement.
Yes. Okay.
Yeah. When
And
it
then it
defines a
maintains.
zero, yeah,
Yes, it doesn't switch. It
exactly.
maintains. Okay.
Yes.
Now that I get it. I get it now.
Okay.
Thank you.
So that is where the difference comes in. So on this other one, which we are calling now return to zero, we have said it uses 3 levels. Like you can see in this diagram, you find that it can use the negative level up to zero. So any bit is going to be represented by 2 levels, like a negative and a zero level, a positive and a zero level, like that. So yes, it is going to switch the same way as the non-return to zero pure, but it is using 3 levels so as to bring about the aspect of synchronization and remove baseline wandering. But what it introduces is more bandwidth, because you will need bandwidth to represent the negative value, the zero value, and the positive value. So it is a good method, but it consumes more bandwidth. That is the only difference. But it has been used because it is better to consume the bandwidth, but then make sure that data, because if it is not properly synchronized, like we have said, if this one of the problems with this kind of a mechanism is that if you are going to have a continuous number of zeros, then you are going to have a problem, or a continuous number of ones. It continues like this. Sometimes the network might sense that there is no data which is being transmitted, or there is a lot of data which is being transmitted and it is unable to interpret it. That is why this method and then and return to zero pure is avoided because of synchronization aspect. But this one with synchronization is very good. So it is the one which has been used to implement the Manchester and differential Manchester. And these are the schemes you will find being used in the OSI model. So if there is one thing the concept you need to understand, the others are still important. You need to understand them like we have done. But now the Manchester and differential Manchester have been practically implemented in the OSI model for data encoding and decoding. And we are saying that in the Manchester encoding, we normally have the combination of return to zero and non-return to zero level. The duration of the bit is going to be divided into two halves, and the voltage remains on one level during the first half and moves to the other level in the second half. The transition at the middle of the bit provides the synchronization. Like we have said, that division in the middle of the bit is the one which provides the synchronization aspect. Then in differential Manchester, it is going to be a combination of the return to zero and the non-return to zero level schemes, whereby there is always the transition in the middle of the bit, but the bit values are determined at the beginning of the bit. If the next bit is a zero, there is a transition. If the next bit is a one, there is no transition, like we had done in the previous one. You remember this one, the one we have said inverted, whereby if the next bit is a zero, there is going to be a transition. If it is a one, no transition. So it's like the opposite of this a little bit. But we are saying that it is a combination of the return to zero plus these two. So hapo ndio nilikuwa nataka uelewe. So when we come to the representation like here, this is the clock which provides the timing aspect or the synchronization aspect. This is the data that we need to transmit. So, like we have said, the Manchester is a combination of return to zero plus non-return to zero level. Manchester, the Manchester, which is now the, what is it called? Differential Manchester, is the one which is a combination of return to zero and non-return to zero inverted. So I hope up to there we are clear. So when this data is being transmitted, look at the first one. Both of them, they are starting at the zero level. So since it is a one, this data, part of that one is going to move from zero to a positive value, then again be translated to a negative value, and then it moves. Then a zero will move from the negative value, move upwards, because this is level. So in the level mechanism, we are going to be moving from one level to another. So a zero, it goes to the positive value, and then it changes midway again, like from negative to the positive value. Then a one, again, we are going to change from the positive level, and the middle of the bit, it goes back to the negative level. Then the zero begins again from the negative level to the positive level. But since we are talking about another zero coming in, it has to start again at the negative level. That is why there is this shift where the bit is changing. and then it begins down there and like that. Hope that is clear. Compare this to the inverted, whereby we are saying 1 again is going to start at this level and then go downward, not upward. It is going downward because we have said it is inverted. So it goes downward to the negative voltage, and then in the middle of that bit, it changes again to the positive voltage. And then we find a 0, which now we are going to move from the positive voltage to the negative voltage, and then shift to the negative voltage again because it is a 1. So there isn't going to be a switch. See, here it was a 1, so it went up. But here it is a 1, but we are not going to have a switch. I hope you can remember here in the notes when we are saying that if the next bit is a 0, there is going to be a transition. If the next bit is a 1, there is no transition. So that is what we are seeing here. Since it is a 1, no transition has happened here. And you move to the 0. Because it is a 0, there is going to be that transition like that. If it is a 1, no transition is taking place. And then we continue like that. Is that clear? Maybe this next diagram can clearly show that, where this is the Manchester and this is the differential Manchester. So where there is no inversion, it is represented this way. Where there is inversion, it is represented this way. So it is the same piece of data, 0, 1, 0, 0, 1, 1. So in Manchester, you are starting from the positive voltage level, and then you come down in the middle of the bit. You are going to provide that switch from positive to the negative level, and then you proceed. Since it is a 1, there is no transition. You proceed like that. The 1 begins from the negative level and moves up again. Since the next value is going to be a 0, then we have said that it remains at the positive side and it continues this way, and the 0 transitions the normal way. But since the next value is going to be a 0, then what happens? There is going to be that change, so that the 0 begins again from the positive side and comes down. Where there is a 1, we are not going to have a transition. In the differential Manchester, we are starting from the negative level because it combines what we call non-return to 0 inverted. So you start from this inverted level and then you move up. In the middle of the bit, you move upward. And since there is a 1 which is coming next, there is no inversion. I think you can notice that. And then you come down. Since there is a 0 which is coming next, there is going to be an inversion where the bit begins, so that it begins at the top and then it comes down. The next one is a 0, another inversion, then like that. Where there is a 1, no inversion is taking place. So I hope that is clear with the two Manchester and differential Manchester representation. Any question? Okay, if there is no question, we can proceed. What are the characteristics? Just like we have explained, the characteristics, they are going to have the 0 to 1 transition at the center of the bit, and that is the logic which is going to provide the synchronization aspect. Then the signal transitions do not occur at the bit boundary, but there is always at the center. There is always a transition at the center of each bit. That is what you need to see. Like here, the boundary occurs only when there is this aspect of switching bits. But any transition takes place in the middle of the bit, like here and here, in the middle of the bit. That is what this one is showing. Then the differential physical layer transmission does not employ an inverting line driver. So where binary bits need to be converted into an electrical signal, you are not going to find the differential physical layer transmission. Why? Because the electrical signal already has the representation. So that is why we are saying the signal on the wire is not opposite of the output encoder. But you will find this in the wireless transmission, then there is going to be that representation. In Manchester encoding, which we also call the biphase, each bit is encoded by a positive 90-degree phase transition or negative 90-degree. That is what we have seen. And then the digital phase locked loop extracts the clock signal and deallocates the value and timing of each bit, like we are showing here. This is the clock which shows how the bits are going to be transitioning at which level in the middle of the bit. That is what we are talking about here. So the transmitted bit stream has to contain a high density of bit transitions. So it is going to consume the twice the bandwidth of the original scheme of the original signal, but it is going to ensure that there is always data is being delivered without any error or without any challenge. That is the benefit of the Manchester encoding schemes. And I hope up to there, we are good with everyone. So the advantage is that the Manchester code is that the DC component of the signal carries no information, and it makes it possible that there is going to be a proper synchronization. So the logic used in representing the Manchester and the previous schemes we have looked at is that a bit is for a 1 or a 0, and it is going to move either from negative to positive volts in the middle of the bit, and for the 0 one is going to move from the positive to negative volts in the middle of the bit. For differential Manchester is that the previous signal before starting of the data, it was set as this was positive, the 0 was at the positive. Therefore, the transition at the beginning, the first bit is set to start from a negative voltage. So the advantages and disadvantages is that the Manchester scheme overcomes several problems associated with the non-return to zero and non-return to zero inverted. The only limitation with the Manchester is that it is going to use a lot of bandwidth. But then we also have some other schemes. We have what we call the bipolar schemes, and these schemes are the ones which are going to have three levels, that is the positive, the negative, and the zero. And the voltage level for one data element is at zero, while the voltage level for the other element alternates between the positive and the negative. So these ones are alternatives to the non-return to zero schemes, and they also have the same rate as the non-return to zero schemes, only that there is not going to be the DC component. So what are those ones? This is the alternate mark inversion. There are still systems which use this one, the AMI, whereby a neutral zero voltage represents the zero and a binary one are represented by alternating between the positive and the negative voltages. And you will see that how that is important. Then there is the pseudo-ternary, whereby the bit one is encoded as zero, and then the zero bit is encoded as alternating positive and negative voltages. So this is how it is seen like. We have the AMI, where we have said that a zero is going to be represented the positive voltage, or a zero is represented as a zero here. And then a one is either going to be a positive or a negative. That is what it means. In the pseudo-ternary, we are going to have a zero represented as a positive voltage, and then a one is either a zero or a negative. So it is going to be alternating between these two. I hope that is clear. How do we detect error when data is being transmitted, or it has been transmitted from the source and it reaches the destination. Like we have said, there could be interferences, there could be noise which affects the data quality. So we can use the sync parity check, the cyclic redundancy check, or the the checksum. The cyclic redundancy check is normally checks the data by attaching a value at the end of that data. So it detects accidental changes to raw data, and these blocks of data entering the system get a short check value attached based on the remainder of a polynomial division of their contents. On retrieval, the calculation is repeated, and in the event that the check values do not match, then corrective action can be taken. So there is an example here. Consider a generator is times 7 plus times 6 plus times 4 and then times and then plus 1. This is how the bits have been encoded. So once they have been encoded like this and they have been multiplied this way, whereby this one is going to be multiplied by the power of 7, the power of 6, the power of 5, 4, 3, 2, 1, and 0. That is how the data is going to be converted when it reaches the destination, because the corresponding binary is going to look this way. So when it reaches the destination, if you have multiplied the data again and you do not get this value, then you realize that something has happened and you either need to resend the data or correct that data. Then we have the other one, which is a checksum. And a checksum is a small sized data which is derived from a block of digital data for the purpose of detecting errors. And this checksum is used to verify the integrity of the data by, how does it work? It is going to have a checksum function, or it is going to have a function by which this data can be checked. So depending on the design goals, a good checksum algorithm usually outputs a significant different value, even for small changes made to the input. And this is very important so that when data has been corrupted, even if it is just part of it, it will be able to detect. And this can be seen in this example, whereby when you have this as the input, you're going to have a checksum attached there. This is also going to be the input and a checksum attached there, the same, and move on. So whenever there is going to be a change, this checksum is not going to work. This checksum value is not going to work. And you normally counter check the data with the checksum value. If it is different, then you know that there has been a problem. Then we also have a variety check, and this is what we also call the vertical redundancy check or the parity check. And here you put a redundant bit, which is going to be added into the data unit. So you could find that here you're going to have maybe the minimum data bit is going to be 8 bits. But as the parity bit, you are going to have the 8th bit as the parity bit, and then the remaining 7 bits are going to be used as the message. So the parity bit or the 8th bit is the one which is going to be put as either odd or even, depending on how the mechanism has been created. And this method, if you have put your parity bit to be either 1 or a 0, and then you realize at the end of the transmission it has been changed, then you know there is a problem. And it can be seen in this example, whereby the minimum, the most valuable number is a P, the parity bit, and the LSB is the one where the data begins. So these 7 bits are the data items, and the parity bit is here. So even parity means that the number of ones in the given word, including the parity, should be even. An odd bit means that the number of ones in the given word, including the parity, should be odd. And this is done by addition. So when you add the bits, you can get either an even number here or a odd number. And that is what you will counter check with when you get to the destination. So that is the explanation on how we check the quality of data that has been transmitted. Thank you for your time.